All right, yes, thank you for coming. Nice to be here. Yeah, I'm going to talk a bit about unlocking underground thermal energy storage, a little bit of a shorter introduction on where we are in the Netherlands, and then I'm going to talk about one of the campus projects that we're talking about. So, yeah, we're all here. So I don't need to tell you that heat storage is a hot topic. Some headlines, reports from the last period in the Netherlands. So many people talk about this, and well, you all probably are familiar with the fact that in the Netherlands we apply quite a lot of aquifer thermal energy storage, and this made me think a bit. So where are we with this technology, and where are we going? So we started with in the 80s. Late 80s, early 90s, and now we're at a little over 3,000 permitted systems, 3,000 roughly operational ATES systems. So really that went from innovation to basically the standard in new buildings. Proven technology, high efficiency, reliable, CO2 reducing. So we're currently a bit in the transition phase to other rules. I already mentioned it. Mainly we use this in newly built buildings currently, individual system, and we're now transitioning a bit towards more existing buildings, so higher temperatures causing more complexity issues in the subsurface, also scarcity of space in the subsurface, more collective systems to optimally utilize thermal energy at different times optimally, and lately, maybe not everywhere, but at least in the Netherlands, we face limited electricity grid availability due to grid congestion, due to the electrification of both heating, mobility, but also on the renewable generation side. And of course, lastly, but not least, the increased cooling demand that we're facing due to climate change. So there are a couple of things that are changing in broader pictures. So seasonal buffering of low temperature heat, check, that's basically what we cover. We keep doing that as we go, but we have still many old buildings in the Netherlands to retrofit. So we want to go to more hybrid system with higher temperatures, and of course this key technology for cooling that ATES is very beneficial for. That comes to some challenges that we're currently working on, and that I would like to tell you a bit about today as well. So there are three main themes. Integration in the wider energy system relates to control and robustness of the integration of these systems, and this strongly links also with what's happening in the building itself. So the building facilities and the heat or cooling distribution inside these buildings. I'm not going to talk about technology development for higher temperatures and optimal sustainable use of the subsurface, so optimal planning and governance of these systems. So a bit about ATES on the TU Delft campus. Here you see a little map of the campus with all the ATES system highlighted. Roughly we have currently 13 or 14 ATES system operational. Most of them are relatively normal ATES systems with a heat pump used for space heating and cooling in new buildings, but there are two special ones. One is the ATES cooling grid, highlighted in blue, and one the high temperature ATES in conjunction with geothermal. Well, a couple of months ago at the European Geothermal Conference there was also a UTES Symposium where I gave a talk, and there I presented about the high temperature ATES in conjunction with the geothermal, so I'm not going to do that again here. And also later in the week there will be some sessions, presentation, contributions dedicated to that project. So I will skip that here for now. I will focus on the cooling grid that we have on the southern part of the campus that's newly being developed currently. So the older part of the campus, old buildings, only heat delivery, we reduced to lower supply temperatures to 90 degrees to facilitate the geothermal use, because otherwise I will get this question, why don't you use the excess heat that we have here in the older part of the country? That is other part of the older part of the campus. Well, that's not possible because here these are newly buildings. We have around 25 degrees low grade heat available. We can use heat pumps to boost this to the 90 degrees, but that's not the most efficient way to do this. So despite the highway that is running also in between these parts of the campus. That question is not needed to be asked again, just to cover that already up front. So we're going to talk about the new part of the campus that we're currently developing. TU Delft is growing a lot with number of students and research groups. So we're expanding the campus. This building is currently being built. This building is recently commissioned. There's quite some other activities going on. So two new education buildings. There are 3 big data centers, new faculty for the physics. There are clean room facilities for the quantum computing. Everybody who knows a bit about building facilities, heating and cooling, you already feel what's coming. There is a huge cooling demand in this area that's currently being developed. That's about 200 terajoules of cooling demand, while the heating demand is only 1/10 of it. So we have 180 terajoules of low-grade heat to get rid of, or 120 terajoules of cooling that we need to harvest somewhere. We tried to find several renewable sources for cooling from water. Drinking water, there's a big drinking water pipe going through. Unfortunately, we would heat it up too much to harvest cool for that. The drinking water company would not allow. Also, there's a big canal. Only that's more or less stagnant water. Also that would heat up too much, which the water board didn't allow. So in the end, we're down to dry coolers. We need to harvest heat from the dry coolers to get that heat and not use air conditioning units. Because obviously these buildings will get IEA systems, and that means that we deplete the cooling, we heat up, we make a big warm well, which we don't use in winter, so we're depleting basically the cooling capacity from the aquifers quite rapidly if we don't additionally regenerate the wells with cooling. And commonly in the Netherlands, these cold wells that are used directly for space cooling, they're charged with around 5 degrees, sometimes 7, but mostly around 5 degrees. So that means that you need relatively low outside air temperatures to harvest 5-degree quality of cooling, to be able to harvest that. And while many people think that the Dutch winters may be cold, it's really a limited amount of hours that we can actually harvest this amount at this temperature level. That would result in very, very large capacities if we would try to meet this 180 degrees, so 180 terajoules. So we came to the conclusion, well, this is not going to work. This is way too expensive, because not only the dry cooler capacity, this would also imply that you need the IEA wells over 6 times as big as we would need for the actual cooling capacity that is there. So we decided to split the IEA system in 2 different ways. One for the space heating and cooling, and one for the process cooling, because process cooling you can also supply at a much higher temperature level, at 12 degrees. And then we have much more hours per year to harvest the cold, to charge the cold well, and in such a way provide the cooling. So how does this look like? In a winter, the normal IEA in the second aquifer will supply space heating using heat pump, charging the cold well at a certain temperature. And in winter we do cold harvesting with dry coolers, charging the cold well, which is more or less also the ambient temperature of the well, and in a deeper aquifer. And then in summer we reverse the flow directions, so we extract from the cold well for space cooling and extract from the deeper, colder well for process cooling. That is the basic concept that we have for this IEA system. This is mainly developed by my colleague Anne Medema and Techniplan, one of the consultants of the TU Delft. But we're now also adding some research to this project, because still this space cooling IEA still has an an energy deficit. It's not in energy balance. We still need to add cooling to that. And also because we have this volatility of the electricity price currently in the Dutch grid, we try to take advantage of that to run the heat pump in summer to provide extra cooling to this cold well to match the energy balance of that system. So just to get an overview of the layout of the system. So this is the whole southern part of the campus. This is the main central part of the heat pump. All the highlighted buildings, they will be connected to this process and space heating ATES systems, and some of the other gray buildings, they have the separate ATES system, but you see here the little, yeah, it's difficult to point it in or maybe I can use the pointer here. You see the different colors with the wells. So these are the really cold wells for space cooling. The orange ones are the in the deeper aquifer. They're the clusters of wells for the process cooling. So my colleague Jana will have also a poster on this session. So if you want to know a bit more on the details on this, you should also see her poster on Tuesday. So we have some preliminary results on this power to cool, where we have some heating and cooling demand from that system, day ahead electricity prices, of course some subsurface data, and we have some rule-based controls on what energy price level we will run the heat pump to additionally charge, cool into the subsurface, in this case a virtual subsurface using ModFlow 6, and then analyze how much of that thermal energy can we deliver to the buildings, and also do some economic analysis on what the actual price then is of the heating and the cooling that is delivered with this system. So you see a plot of the well temperatures. Oh, I should stop pointing that with using this. Here you see a plot of the well temperatures. The black lines are the ones where we do not use power to cool. And the dotted lines here you see when we use power to cool at a price level of minus, so negative prices, and we go up to 10, 20, 30 euro per megawatt hour. And you see that the first step, so already starting with power to cool at negative prices, already causes a nice jump down in the cold well temperature. Additionally, charging at higher prices also helps a bit, but less so. Well, eyeballing temperature graphs is always nice, but we want to see the real numbers, of course, related to the cost of heating and cooling. Well, here you see how the power to cool also helps to reduce the levelized cost of energy that is per megawatt thermal cooling capacity provided by the system. So these are still small, but also not negligible changes in the price. Again, these are preliminary results, so there are quite some limited hours here that we can actually charge still at those changes in price threshold. So there's room to optimize for, also if we, for example, use a higher capacity heat pump for this. Also the heat price decreases. As you see here, you have to ignore this for now because there's some oddity in how we transferred also the temperature to the warm well. There's something that we work on, but there's still clearly some potential. So if you also can use the heat and store that at higher temperatures that you get from the condenser when you run the heat pump, then there's also a benefit for the heat price, clearly. And as you saw in the wells, we have multiple well clusters. So in this system, we potentially can simultaneously charge cold and warm wells, which is of course not possible if you only have one cold well and one warm well. All right, so these are some preliminary takeaways. So the power to cool considerably reduces the levelized cost of energy. may also reduce the cost for power to heat, for the heating price, but this is all ongoing research for the coming years. This is part of the Max Flex project that we're currently working on with these partners, which is now roughly 1 year started and 3 years to go, so still many more analysis to come on this. So some of the innovation highlights that we have in this project, and so we use the UTES primarily for cooling at different temperatures and try to optimally integrate that in the electricity grid. So take home, via research and demos we try to develop to novel, cheap, robust UTES innovations, in this case mainly ATES innovations, and by doing so also use the subsurface sustainably. There's still some challenges ahead that I didn't discuss, but these relate to the general challenge that we have, so the upscaling both in temperature level, placement density. As you see, this is quite densely placed already here. The integration in the wider energy system, the performance, make sure that the system optimally perform, and obviously also market conditions to be able to optimally leverage price variations. So UTES is in transition, so we have scarcity of subsurface space. We need to optimally organize this. Existing buildings, more complex subsurface conditions which we need to cover. There's some nice graphs from a paper of Stein that is almost published. The integration in the electricity grid, and of course the increased cooling demand that is part of the challenges that we face the coming years. And with that, I'd like to close and acknowledge the many people that I collaborate with in some of these projects.
Yes, thank you, Martin. Looking at the future that we are heading towards, that the cooling gets even more and more. So this is very good that you actually start to model this out and have a project on this on the TU campus. We have time for one question. Yes.
Yeah. Thank you so much for that. Very interesting. I was just wondering if as you're considering these retrofits and all of these challenges, are there kind of buildings that are low-hanging fruit, really easier to retrofit than others, and on the other side, are there buildings and use cases that are going to be kind of more challenging? Or is it more based on the subsurface of, the more challenging subsurfaces?
Well, that's that, of course, there's a great variety. We have 8 million existing buildings in the Netherlands, and most countries, even much more, and the variety is great. So the low-hanging fruit is really in the bulk buildings, the apartment buildings. That's really low-hanging fruit. Old city centers, poorly insulated. That is, of course, much more difficult. Also, if it's corporation owned, then it's much more easy to collectively insulate and switch the energy system, change the energy system, than if it's all privately owned, because you need to bring along all the people. They need to commit to such a system if they own the building. So organizing that is very difficult. You have to go house by house by house. At least in the Netherlands, maybe other countries can enforce connections. Maybe we should at some point. Otherwise, we will not make it probably to fully decarbonize 2050.